Hi everybody, this is lecture 8 and today I'll tell you about change of variables in double and triple integrals. So we've done this before. We've changed at the beginning of this quarter. We changed variables. You have changed variables from Cartesian to polar coordinates, for example, because some problems are easier to describe in terms of polar coordinates than they are in terms of Cartesian coordinates. And we also changed variables in 3D, going from x, y, and z to r, theta, and z, or that is cylindrical coordinates, or alternatively, you also computed integrals using spherical coordinates. Okay, so what I wanted to tell you today is how to work with coordinate systems other than these three these three special ones that I told you about, right? I told you how to work exactly how to set up integrals in polar coordinates in 2D or in 3D in cylindrical and spherical. Today I want to show you how to, if you have given a new coordinate system that might be the best possible coordinate system to tackle the problem you have. If you just know, given a coordinate system, how to integrate using that coordinate system. Okay, so let's do that. So before I give you the general setup, I'd like to think about what we do in the case of polar coordinates. Think through revisit the process of setting up an integral using polar coordinates. So as to have each stage clearly explained and set clearly in our heads in this familiar situation, because then I think that'll guide our discussion in the general setup. Okay, so let's review setting up integrals using polar coordinates. So let's say we have a region of the xy plane. I'm going to squeeze the xy plane here on the side. And our region is going to be one that's nicely described in terms of polar coordinates. So for example, 1/8 of a disk. So here's the region. It looks like a pizza slice. We'll call it R. So 1/8, this means that this angle over here is pi over 4. So the angle goes from pi over 4 to pi over 2. And the radius of this pizza slice is, of this disk is 1. So we're talking about a quarter, an eighth of that disk. Okay. Now when we set up a double integral over this pizza slice, often we will want to change coordinates to polar coordinates. So here are polar coordinates r, and actually let me put theta down here, theta and r. Right, often we'll want to, instead of doing the double integral over r, we actually evaluate, over this region, capital R, we evaluate a double integral with certain bounds for r and theta, right? The bounds would be, in this case, I would say that theta goes from 0 to pi over, theta goes from pi over 4 to pi over 2. And r goes from 0 to 1. So the region of integration in the r theta plane is a rectangle. Right, when we set it up in terms of polar coordinates, we're actually doing a double integral over a rectangle. So this rectangle over here. Okay, so when we change to polar coordinates, we're really integrating over a different region. So I'll call so we're integrating over the region of the r theta plane that corresponds to r. So let me just say that, let me call that region S. And there's another important thing when we change coordinates to polar coordinates, and that's the rule for changing the coordinates, right? So if I give you a point if I give you r and theta, you have to know what's the corresponding point in the xy plane, right? So if there must be a way from going from r and theta to x and y. So that's an important ingredient. This rule, this transformation from r and theta coordinates, from points in the r theta plane to points in the xy plane. So the point corresponding to r comma theta has x equal to r cosine theta and y equals to r sine theta. Right, so this first component here is x and the second component is y. So that's something that we need when we set up the integral. When we evaluate an integral over r in terms of dr and d theta. Okay, so and then there's two things we change when we move from an integral of r to an integral over s. So we have to change the function. We start with the function of x and y, and we actually integrate a different function of r and theta. To get that function of r and theta, we substitute these formulas for x and y in the original function, and then we multiply by a scaling factor, right? So here's why we multiply by that scaling factor. So when we do the double integral over this region S, we're doing two iterated integrals, and the integrals are approximated by Riemann sums. So we're really breaking the region S into a bunch of little rectangles like this, right? The width of a rectangle is an increment in theta, delta theta, and the height is an increment in r, delta r, right? So if I have now, so I have these little, you end up breaking S into these rectangles. Now the area of this, so this subdivision of S corresponds to a subdivision of R, of the pizza slice, right? The horizontal lines are the constant R lines, so constant radius. This gives me a bunch of circles, constant circles about the origin. And the vertical lines, those are the constant theta lines. These are rays shooting from the origin, like this. So I have a 1, 1, 2, 3. So let me just draw 3 subdivisions here, like this. Oops, no, it doesn't look too right. And if I look at a particular square in S, it corresponds to some square, maybe this one here. Not really a square, a curved, kind of almost very. If we're talking about a small rectangle on this side, we're getting something that resembles a parallelogram on the other side, a curved rectangle, if that makes sense. Okay, and but the point is that if r is bigger, then you get bigger regions of the xy plane, and if r is smaller, you get smaller regions of the xy plane. And the thing we worked out is that the area, so here, that the area on this side is when we move to infinitesimals, when these squares are really small, the area on the xy plane, so that's in terms of coordinates x and y, is r times dr d theta. So and the key thing is that you have to multiply. So dA is r times dr d theta, not just dr times d theta, because dr times d theta represents area in the r theta plane, and not area in the xy plane. But if we multiply that by r, we get area in the xy plane. Okay. Now let's look at the general situation. So in general, we'll have. We're going to have some region of the xy plane, and we're going to have a region of, so we're going to have new coordinates, u and v, right? So I'm going to start with a certain region of the xy plane, maybe this one, and there is a rule for going from u and v to x and y, right? I need to know, so to say that u and v are coordinates on the xy plane, I have to tell you what's the point in the xy plane corresponding to a point in the uv plane given u and v. So this is going to be a map, a certain transformation t from the uv plane to the xy plane. So it should tell you, if you know u and v, it should tell you what's the corresponding x coordinate and corresponding y coordinate. Right, so in the previous example, x of r and theta was r times cosine theta, and y of r and theta was r times sine theta. And then so the goal would, given a possibly complicated shape R, the goal would be to have a coordinate system, a new coordinate system U and V, where the region corresponding to R is simpler. So let's say maybe I'll draw another. I mean, in general, it could be a complicated shape. I'll draw S more round than R. So ideally, S would be simpler than R, and then it's easier to set up an integral over S than it is to set up an integral over R. Right, but the key is that when I change coordinates from x and y to u and v, I will be integrating over a different region, the region of the uv plane that corresponds to R. So the sets of points u comma v that give you points x and y by this rule t over here, right? And remember, in the example, the original rule was this. So our job for the next few minutes is to understand how dx dy compares to du dv. So this is our job for now. This is our next job, dx dy versus du dv. So before we learned, so for example, when u is r and v is theta, then this scaling factor, this change. So I want to know if the relationship between the area of a little rectangle in the UV plane and the corresponding curved rectangle, if that makes sense, inside R. Right, this scaling factor, how much bigger or smaller this curved rectangle compares to this one. Okay. So let's think about this for a while. I'm going to zoom into this, just like when we were discussing surface area. So let's zoom in. So we have on one side the xy plane, and on the other side we have the UV plane. Right, and I have a rectangle in the UV plane. So I'll say that this point over here is the point, it's going to be important for us, so let me give it a name. So U0, V0. Now let me draw the corresponding region of the xy plane. So remember we have a transformation T, a formula for x and y. Formulas for x and y, two formulas, one for x and one for y in terms of u and v. So according to this rule, there's a region of the xy plane that corresponds to this rectangle, and that region is going to look something like this. Okay. And so we know, for example, so let me just give everything names here. So the width of this rectangle is going to be delta u. The height is going to be the change in v, delta v, right? So delta v is the change in v, the coordinates. So if I go from here to here, I'm increasing the v coordinate by delta v. If I go from here to here, I'm increasing the u coordinate by delta u. And another thing I'd like to give a name is the area of this thing. So this is area delta A. And I'd like to understand what delta A is in terms of delta u and delta v. Okay, so here's how we're going to do this. I want to have a good approximation for this area. And here's an approximation that's going to be good enough for our purposes. So I will use these two vectors. Look at these two vectors. So let me call the one below A and this other one B. So for example, vector A is just the coordinate of this point minus the coordinates of this point. So this point corresponds to u0, v0, and this other point is the point in the xy plane that corresponds to this point over here. Let me write the coordinates for this other point. So this one here is the same height, still at height v0, but the u value is different. It's the original u value plus delta u, and the height is just v0. Okay. All right, so A is this point, so t of this minus this point, which is t of this. So let me write that down. A is t of u0 plus delta u v0 minus t of u0 v0. All right. Now, let me give you a good enough approximation for our purposes for finding this, for understanding the area, understanding this area. So a good enough approximation for us will be this, will be to say, so A has an x coordinate and a y coordinate, right? So this vector here, this vector A has a y coordinate and an x coordinate. So what's this x coordinate? It's the, so we're looking at let's just look at the x coordinates of these 2 points, right? So this is x of this value, this over here is x of this value, right? So I'm fixing the y coordinate, sorry, the v coordinate, and increasing the u coordinate by a little bit. So by how much does the x coordinate change? And the answer is given to us by a partial derivative. So the x coordinate of A, so A is going to be the change in x, the partial of x with respect to u, evaluated at the point u0. Let me just note that in a second, separately. So times delta u plus the j component. Let me just recap this. So the I component of A, so the width here, that's so it's the x coordinate here minus the x coordinate here, so it's x of this minus x of that. When you look at this difference, the second coordinate is fixed, so it looks like a partial. I'm evaluating x of this u value minus x at the original u value. So that would be, if I were dividing by delta u, I would get something that in the limit is the derivative, but since I'm not dividing and multiplying, I have to put that delta u back in. So I'm just, the derivative times delta u gives me the x coordinate of A. X of this minus x of that. Now I should be careful here. So this is evaluated at the point, so x is a function of, so this transformation is really is 2 functions, remember, so t of u and v is some, has x and y coordinates. So these x and so the point corresponding to u v has an x and a y coordinate, and these coordinates depend on the values of u and v. So we have really 2 functions, and I'm taking a partial of the first function evaluated at this point over here at u0 v0. And now for the height of this, for the I component of the vector A, it's just the y value here minus the y value there. So that's for the same reason, dy du times delta u. And this is also evaluated at u0 v0. Okay, so that's the vector A. So this vector, so we're getting close to finding this area delta A. Now, so because delta A looks like the parallelogram spanned by A and B. So let me first understand B before we get to the area. So so this vector B is t of, so it's this point minus this point, so that's B. It's t of this point minus t of that point. And you see that these 2 points have the same x coordinate, but the v coordinate changes by delta v. So that's this b vector is approximately So what's happening in here is so dx, so the change, so these two x, so this difference in the x coordinates is dx dv. Sorry, you take the v partial of x with respect to v, multiply that by delta v. That's the I component, and the j component is the v partial of y multiplied by delta v times j. So exactly the same reasoning as for a, but you notice that here we're looking, instead of differentials, so instead of seeing t of this minus t of that, we're seeing t of this. So b is t of this minus t of that. So we're looking at the different values of x, the difference in the values of x and y when u is fixed and v is changing a little bit. And so you get v partials instead of u partials. And so delta A is, let me do this with some room more space to write on the next page. So the area, so this area over here, so the area in the xy plane that corresponds to this little rectangle in the uv plane, so that's approximately the area of the parallelogram. So let me just write this, the area of the parallelogram spanned by A and B. Parallelogram. Okay, spanned by A and B. Now this area, the area of this parallelogram, is plus or minus the determinant. The determinant of the matrix with rows A and B. So let me just do this. Plus or minus the determinant of a 2 by 2 matrix. Oh, let me put a plus or minus here. Plus or minus the determinant of a 2 by 2 matrix, where A is in the first row and B is in the second row. So A, is that okay? So I'm saying that in general, if you have two vectors in the xy plane, if I want to know the area of the parallelogram spanned by the two vectors, I can just make a matrix with the two vectors, put A in the first row, B in the second row, and take the determinant, and this is plus or minus the area of the parallelogram. So we discussed this in 3D, and we also discussed cross products when we were reviewing vectors. From our discussion of cross products, you can derive this fact, that the determinant, if I put A and B in a matrix, if I put two vectors in a matrix to make a matrix, the determinant of that matrix is the area of the parallelogram. So let me just use that fact here. So the components, the components of A are these two. So let me give myself some space. So that's dx du times delta u. That's the first component of A. Then dx dv times delta v. That's the second component. Oops, that should be dy delta u. So this is A. Now let me put B here. So that's dx dv delta v, dy dv delta v. Okay, now let's evaluate this determinant. So you just do the multiplication here. I'm going to get so the plus or minus, so because we're talking about an area, I can put let me just leave plus or minus for a second. So it's plus or minus a number that'll denote dxy comma duv. And then you see that there's delta u delta v, then delta u delta v in the other way, so I'll just write this here, delta u delta v out. So this determinant over here, it's dx du times dy dv minus dy du times dx dv. So this is called the Jacobian determinant. Okay. Let me change one thing in this formula. So I'd like to just replace this plus or minus by an absolute value. So I'll just put an absolute value here. So the absolute value is because the area is always positive. So you just want to make whatever this determinant might be negative, but if you put an absolute value, it's always going to give you the right sign, the sign you want. Okay. So if you'll give me a second. So our conclusion, so the conclusion is this. So the area element in terms of u and v, so the area element in the xy plane in terms of u and v is the absolute value of the Jacobian determinant times du dv. Okay, so this derivation was very theoretical and it might feel abstract. So I want to bring this down to earth. So let's see what this does, this whole Jacobian determinant business, what it does when we're looking at the case we're familiar with, when we're looking at polar coordinates. So let's do an example. Let's do that example. So let's say that x is r cosine theta. So u and v are r and theta, and y is r sine theta. Okay, I could say that u is r and v is theta, or I could say that u is theta and v is r, but here I'll just, say that work with r and theta in terms of u and v. The names of the variables is not important. So now what's the Jacobian determinant? So du dxy over dr theta, that's the determinant of, this is not looking so pretty, I can move things down. Okay, so that's the determinant of dx dr, and then dy dr, then dx d theta, dy d theta. So this determinant, in this case, we have to compute these partials, right? So dx dr, so in this case, x is r cosine theta. So dx dr, for example, is, if I take the x partial here, I'm just left with cosine theta. So let me continue this calculation on the next page. So we're looking at the determinant of, so dx dr is just cosine theta. R partial of x is cosine theta. The r partial of y over here, this is y partial of r sine theta is just sine theta. Okay, let me write that. Now let's look down here, dx d theta. So the theta partial of, so as far as the theta partial is concerned, r is a constant. The derivative of cosine is minus sine, so I get minus r sine theta. Let me write that down. No, forgot something. So minus r sine theta. And finally here, dy d theta is r cosine theta. Okay. Now if I do this determinant like this, I'm going to get r times cosine squared theta. So there's going to be an r on both products. So I'll just put the r outside. So r times cosine squared theta minus sine times minus sine. So the minus becomes a plus, sine squared theta. Okay, so is this equal to, so in the beginning of the lecture I said that we know that this is equal to r, and that's the case, right? Because so this Jacobian determinant business gave us the right answer because cosine squared plus sine squared is equal to 1 for every angle. Whew. All right, so this is encouraging, right? The volume, so the whole Jacobian determinant business gave us the correct stretching factor, scaling factor in the case that we're familiar with. All right, so now I would like to do another example, one that's closer to homework and exams. So here's the example to close today's lecture. So just to give you, so we know where we're going. So next up, I would like to do a very practical how to do this, how to use the change of coordinates in a calculation. Do a very practical calculation with you, and then I'd like to make a few remarks about what happens in 3D. But I'll just show you a formula. I won't explain it too much because one, it's really close to the 2D situation, and two, in exams and homework, you won't be asked to do 3D, not because it's any harder, but because it takes the determinant of a 3x3 matrix it takes longer to do, and setting up the matrix, computing a bunch of partials also is a little bit boring. So you don't have to bother with the 3x3 case, with the three-dimensional case. Okay, so example. So our job is to compute the double integral over a certain region R of this function, e to the x plus y over x minus y, with respect to dA. Right, dA. So R is a region of the xy plane. The dA is the area in the area element in the xy plane. And we're supposed. So I'm going to draw the region in a second, but let me say that we're supposed to compute this integral using these new coordinates. So u is x plus y, and v is x minus y. Okay, so these are going to be, maybe I'll put them like this. Bring v down here. So our job, I'm going to draw this region in a second, but let me just say what we have to do. We have to compute this integral by changing coordinates, changing to u and v rather than x and y. And so can you guys see u and v? If I give you a point in the plane, x and y are, the x and y coordinates are numbers you attach to that point. I can also attach to that point the sum and the difference of x and y. These are two other numbers, and I can also use those two numbers to identify my point. Right, these two functions are independent. It turns out if I know u and v, if you're smart, you can, this is actually a bad way to say it. If you know u and v, and you can pick up, you can figure out x and y. So that's the test for a new coordinates when two functions give you a coordinate system. Let me show you. You can go back and forth between u and v and x and y. So what I'm going to do is I have these two equations. So I'm going to solve, find x in terms of u and v using these equations. And a quick way you can do that is just add the two equations. And then if you add the two equations, you get that u plus v is equal to 2x, right? If u plus v is equal to 2x plus 0. And if I subtract the two equations, so u minus v is equal to x minus x, so that's 0, then y minus minus y, that's 2y. Right, and here you guys can see that I can express that x is just a half of u plus v and y is a half of u minus v. So if I know x and y, I can get u and v by these formulas, and if I know u and v, I can get back x and y by these other two formulas. So u and v are valid coordinate system in the xy plane. Okay. So the problem to evaluate this integral by changing coordinates to u and v is going to be doable. So let me finish telling you what the problem is. I have to tell you the region of integration, and the region is going to be this. So it's going to be this region. So let me draw mark a few points here. So that's 1, 2, so -1 and -2. So our region is here. Right. So these parts, these four, we have 4 line segments joining these 4 points. That gives us our region of integration. Okay, so let's do this one step at a time. Let's evaluate this integral once by changing coordinates one step at a time. So one thing we need to do is to compute. We certainly need to do is to compute the Jacobian determinant. So let's do that. So so the Jacobian determinant dxy over duv is okay. So let's see. So up here, let me just draw everything. So that's dx du, dy du, dx dv, dy dv. Oh, oops! I meant to write determinant of. So let me also do a few things. Let me just get formulas for x and y. So x is a half u plus v, and y is a half of u minus v. Right? I'm just taking these 2's and moving them to the other side. All right. Now what's the u partial of x? So here I have x and y expressed in terms of u and v. So the u partial of x is just a half. Okay, now the u partial of y is also a half. Okay, the x partial of the v partial of x, again a half. Oh wow. Okay, again a half. And finally the v partial of y, that's minus a half. So when I do this determinant, I get minus a quarter minus another quarter, so that's minus 2 quarters, that's minus 1/2. This is a crucial piece of information. The Jacobian determinant is minus 1/2. Okay, so our integral, so let's go on and start evaluating the integral. So that's going to be, I'm going to draw a picture on, well, okay, never mind. So here's what we already know, that the double integral over over this shape R over here of the function e to the x plus y over x minus y with respect to dA is equal to a double integral in terms of u and v. So the bounds, the region of integration we'll figure out in a moment, but it's going to be the region. So S is the region of the UV plane that corresponds to R. I'll show you how to get that in a second. Now the function we're integrating is e to the u plus x plus y. So in terms of u and v, x plus y is u and x minus y is v. So that's e to the u over v times the Jacobian determinant in absolute value times du dv. Now this Jacobian determinant in absolute value, so the Jacobian determinant is minus a half, so here it's just equal to 1/2. So this scaling factor is equal to 1/2. So this is telling me that area in, if I take a little rectangle in the UV plane, the area of the corresponding region of the XY plane is going to be a half of the area of that little rectangle in the UV plane. Okay, so we're almost ready to evaluate this, right? This looks very, manageable. But before we evaluate this, we need to understand what the region of integration is. So let's do that. So I know, well, here's a good method that works in a great number of examples. So I'm going to understand what the region S looks like, I'm going to use some equations to understand what R looks like, to describe R, and then translate those equations to U and V. And then, so just write a description for R in terms of X and Y, translate that description to U and V, and then try to draw that. Try to understand that description in terms of U and V. So let's put a few equations to this picture. So what's the equation of this line over here? So this line, so let's see, it looks like the diagonal where it has slope 1. So here you move 2 units to the side, and in the x direction, and y increases by exactly 2 units. So this has equation y equals x, but when x is 0, I get minus 2. So that's y equals x minus 2. All right, let's find an equation for this side over here. I can write it over here. So this other line, same deal, has slope 1. You move 1 unit to the right, you go 1 unit up. So the equation is going to be y equals x, but then it's minus 1 because when x is 0, then y is minus 1. All right. How about this equation over here? So what about this side over here? So this one has easy equation, y equals 0. And finally, this side over here is just part of the y-axis that has equation x equals 0. Okay, now, so these are 4 equations. These are equations for 4 lines, and so if knowing these 4 lines, we can recover the region R, right? It's bounded by it's a region bounded by these 4 lines. Now let's translate all of these equations to U and V in terms of U and V. Okay, so so this first equation, let me do something here. So the first equation is y. So this first equation, y equals x minus 2, I could write it as x minus y equals 2, but x minus y is v. So v equals 2. Can you guys see that? So this here can be rewritten as, so the thing in red can be rewritten as x minus y equals 2. And then x minus y is equals 2 is just v equals 2. So similarly, the one here at the top is x minus y equals 1, which is v equals 1. Okay, next let's look at this equation over here. So y equals 0, y is u minus v. So u minus v equals a half of u minus v. A half of something being 0 is the same as saying that that thing is 0. So u minus v is 0. In other words, u is equal to v. And this other equation over here, x equals 0, is saying that u plus v is 0. If x is 0, then u plus v is 0. That's to say that u is equal to minus v. Okay, so now we have equations for the sides of this region R, so we can use these equations and translate it in terms of u and v. So let's draw the curves that make up this. Let me draw these lines in the UV plane. So for example, this one over here is just v equals 2. So in the UV plane, let's draw the UV plane over here. So I know I'm not going to need negative values of v because I rehearsed this lecture. So v equal to 2, let's say that's over here. So that's one of the lines. So this line over here is the same is the line that corresponds in the UV plane to this diagonal line in the XY plane. Similarly, this line over here is just given by v equals to 1. So it looks like this. Here, v is equal to 1. Okay, now this line over here, u equals minus v, so it contains 0, 0, and it's anti-diagonal, like this. So this line over here is u equals minus v. This over here is v equals 2. Down here I have v, maybe, I don't want this picture to be confusing, but this is v equal to 1. The final segment, this one here, has equation u equals v, so in the uv plane it's diagonal. And so the region, so the original region R was bounded by these 4 lines. The new region is also bounded by these 4 lines. So that's our mystery region R. That's our mystery region S, the region of the UV plane to which R corresponds. Okay, so now we can get. Let me write the equation here. So this is u equals v. Okay, so now we're in business. We can do this calculation. So here's what we can set up the double integral. So I'm going to set it up in the order I want v to be outside, and then for an intermediate value of v, I want to go from here to here. So u inside, v outside. So the order will be du dv, which is also actually the order I already wrote there. So let's integrate v from 1 to 2. So from here, so this is the minimum value of v in S. This is the maximum value of v in S. Now, and fix an intermediate value of v, like here, and then do an integral like this. And so u is starting at minus v and stops at plus v. So u starts, or when u starts, it's equal to minus v. When u stops, it's equal to plus v. Okay, then we're integrating the function e to the u over v times a half du dv. So the answer will be a half of something, an integral in v from 1 to 2. So now the inside integral, that's the integral of e to the something, that's going to be so it's going to be e to the same thing. So the integral of e to the u, if we didn't have a v here, the integral of e to the u would be e to the u with respect to u. Now we have a v, so let's just modify that. So let's look at the primitive e to the u plus divided by v. Let's differentiate this. I'm going to get e to the same thing multiplied by the derivative of what's inside. The derivative of what's inside with respect to u is 1 over v. So if because I don't want to see that here, I'll multiply this by v. Okay. Okay, oh, I got a little bit confused here. Still have to evaluate this with u going from minus v to v. Okay, now let's see what we have inside. So in the top end, u is equal to v, so I have e to the v over v, that's e to the 1 times v minus, then at the bottom end, u is equal to minus v, so I get e to the minus 1 times v. So that's really a constant times v. So I get, so this whole integral is e 1/2 of e minus e to the minus 1, that's 1 over e. Then integral from 1 to 2 of v dv. So it's 1/2 of e minus 1 over e. The integral of v dv is just v squared over 2 between 1 and 2. That's 1/2 of 4 minus 1. That's 3/2. I had another half over here, so I get 3/4 of e minus 1 over. So that's it. That's how you do. That's how you transform an integral in terms of u and v given to you in terms of u and v to the in terms of x and y. That's how you change the coordinates to u and v and finish up the calculation. So the coordinates u and v were good for this problem because the function became simpler in terms of u and v. The Jacobian determinant was manageable. It was just a constant, a half. It's fine to integrate. And because the original region was, in terms of u and v, remained manageable. So I was able to set up this the double integral over s without much trouble. So sometimes, this was a good choice, a good good idea to change. It was a good idea to change coordinates from x and y to u and v. So in general, if you're looking for a coordinate system that's good for a particular problem, you should look for all of these properties. You should think. So in some problems might ask you to compute an integral using an appropriate change of variables, and then it's your job to to decide which change of variables to use. So my recommendation is you should look for expressions that appear in the function you're integrating. So combinations of x and y that appear throughout, in the function you're integrating, and try to see if you can express the region of integration in terms of the same combinations. So here in red, it would have been better if I had written x minus y equals 1, x minus y equals 2, and the other two were also okay in terms of, nicely expressed in terms of u and v. So my recommendation is, if you have to decide by yourself which coordinates to use, you should look for expressions that appear in the exponent, combinations of x and y that appear also both in the exponent but also in the region, in the description of the region you're integrating over, and then then using those expressions, those combinations of x and y as your new coordinates will probably simplify the integral for you. Okay, so the last comment I wanted to make is what happens in 3D, is about what happens in 3D, and here's the answer. So in 3D, everything is the same, except that if I have a new coordinate system, so if instead of x, y, and z, I have a new coordinate system in 3D, that new coordinate system is going to need 3 numbers to describe points. So those 3 numbers I could call u, v, and w. And so the new coordinates will have three numbers, but other than that, everything is exactly the same. So you set up an integral like this, with all the partials, take the u partial of the 3 variables, v partial of the y of all variables, and the w partial of all the variables, and then to take the absolute value of this. So this determinant here is plus or minus the volume of a box. So put the absolute values to get the volume of that box, and by a very similar argument to what we've discussed, volume in the xy plane is volume of the standard box times du, dv, dw. Okay, so thanks for listening, and I'll see you guys next time.